Now I'm going to do some considerations with regards to the inverse square law. You see here I've got a candle with a square piece of paper cut out with the diagonal lines run through the middle, and mirror imaged it. So you've got a series of three there. I'm only going to deal with the first two and see what kind of mathematics and all spatial considerations we can make. See if we can discern where the inverse square law lies in this scenario. I'm going to mark this. I'm going to mark each square, the first two squares that you see, I'm going to mark those onto the TV screen. Then after do that, I'm going to demonstrate some things that happen when we start moving this whole scenario different directions, and to illustrate how hard it is to calibrate this, because the least bit of movement right, left, up, down stretches the squares, adds to their length measurement or detracts from their length measurement. If I move the candle, if I move the TV, if I move the computer, all those little motions affect the measurements of these square sides. So I'm going to mark these as close as I can, and then I'm going to demonstrate what I'm saying about the stretching and the difference in length measurements that you get based on the slightest alteration of motion. And we can consider the slightest alteration of motion would be the slightest deviation from one point of relative view to another point of relative observation. I've tried to center, you see, I've tried to the best of my ability to center these two squares. The reason why is because if we don't have them centered and we go in and make our considerations, then we have to geometrically take out all the deviations from these two being parallel, because that's one of the relevant things here. True parallelism seems a lot more easier to discern the golden ratio as well as the inverse square law. But if they're off the least little bit from true parallelism, then all the measurements start to deviate. Not significantly, but start to deviate. So if I can do this versus having the second square move to the right or to the left too much relative to the center of this one, then we won't have to go in here and geometrically line up the centers. I probably still haven't got it exactly because it's almost impossible, like I said, given the slightest motion of this whole component system here. So what I'm going to do is I'm going to try to highlight these squares onto the TV screen, then we'll have a reference. Again, trying my best not to move and trying my best to represent these. Right now it may look a square, but actually it's a little bit off, and actually the bottom side is a little bit stretched. I have to approach this from the other side. Again, even moving on the floor, as you see, affects the motion. So really, if I had the ability to keep everything still with no motion, the least bit of motion is throwing these things off a 64th of an inch, a 32nd of an inch. show you how sensitive this is. Virtually impossible. Well, impossible. If I move, you'll see these lines go up and down. If you pay attention to if you can see them on the screen. Let me just start just barely moving this camera, and you'll see with the least bit of motion what will happen. See, it's coming off of the line there. Just the least bit one way or the other. And this is starting to teach us something about relativity and how it affects what a person is seeing relative to another person who sees the same object. The slightest bit of motion from one relative observer as observing an object will present a slightly different geometric value than a person who's looking at it from another angle, who may or may not be undergoing slight deviations in motion, relativity. Okay. Now watch, if I move the computer just the least little bit. Now another thing I want to demonstrate as far as relativity, length contraction, expansion of a line, the stretching of geometric shapes. If I move this, if I take the measurement of this second one here, and I'm going to take that measurement real quick, represents approximately 1 7/8. Now watch what happens. Even if I try to keep it horizontal and go straight across, when it goes straight across, now I've got almost 2 inches. Now I've got a little bit more than 2 inches. This is a very quirky thing, this thing called relativity. Now if I have that object there, again we've got about 1 7/8. But if I go up, we have a measurement of almost 2. I go down, it's dropping below. It's almost down to 1 3/4. This main one square here, the bottom square, is about 3 13/16. 3 14/16. 3 1/4. 3 3/4. So the slightest bit of movement stretches those and changes the linear measurements of those sides. 1 3/4. Added 1/8. Drop down. Let's watch this. Now let's move the computer. We're basically right in the line there, but if I move it off, as I move it, changes the linear measurement of the sides, width or length or height. That makes this a very hard experiment. So what I'm going to do now is bring the camera over, and you can see my marks there. I'm going to make those more distinct here. And again, it's hard to line this up, seeing as I drew this on the TV and I've got to go by the I've got to try to frame this in. Got a slight deviation there on the corner. I can only get it as best I can. And we got a slight deviations there. So I don't know whether to go with the top line and follow it, or whether to go with the bottom line and leave the blue up top. So all these little anomalous things that happen when you're trying to set up the experiment with limited resources makes it very hard to get it to where I can clearly see the math for the way it is. We'll leave it about right there. Again, our measurements, our mathematics is not going to be on. Let me do that again. Okay, I went with the, okay. See up top, see how this line's angled in? Well, this line is too. So seeing that they're the same shape, what I'm going to do is I'm going to go with the top line the same way I did here. I'm going to bring it straight down versus going at this point and going up and bringing the blue in here. There we go there. Now I'm going to go ahead and copy these and bring them over here to where I can work with them. Now that I've got it still to where it doesn't move, now I can work some. This would be impossible to do, to try to make all these measurements and do all this with while it's video and on the screen. So if I take it into Paint, try to the best of my ability to represent what I drew with a magic marker the same way, now we can make some mathematic considerations. You see what I've got there? And we're going to compare make all the spatial considerations, distantial considerations, length, width, proportion from this one, etc., and see if we can see if there's anything relevant produced. I'm going to stop the webcam here, do some work with this, and then bring this back into the next video.